Assalamu alaikum. Today we will talk about partially ordered sets. Now, previously we have talked about what? Previously we have talked about sets. We have talked about their binary relations. We have talked about. We have also discussed the important properties or basic properties of these binary relations. We have more specifically looked at the equivalence relations. And then we have also showed that equivalence relations and partially partitions are closely related. So equivalence relations and partitions are closely related. And then now we will talk about in this section we will consider binary relations which are reflexive, which are transitive, and satisfy new property called the entry-symmetric. So equivalence relation is a relation which is reflexive, symmetric, and transitive, right? Now, in this section, to talk about the partially ordered sets, we will introduce a new property which is entry-symmetry. Okay, perfect. So let's start by defining a definition. So definition 1.4.1, and it says a relation R on a set S is called partial order called a partial order on S if it satisfies the following conditions. Number one, the order pair A comma A inside R for all A inside S, or you can say R is reflexive. A is A R related to A. You can also say that. Number two. Number two is that for all for all A comma B inside set S, if A comma B is inside R and B comma C is inside R, then A comma C is also inside R, which is same as saying that R is transitive. Okay, this should be number three, which I have mixed it up. So let's pick this up and then put it here This is 3, and number 2 is actually that for all a comma b in S, if a comma b is inside R, relation R, and b comma a in inside relation R, then A is B. And if this is true, then R is anti-symmetric. This is a new condition. If A is R related to B and B is R related to A, then A is B. And if this is the condition, then R is anti-symmetric, not symmetric. If R will be symmetric if A is not B, but R will be anti-symmetric if A is B. So these 3 conditions will create partial order on a set S. Okay. And in other words, if a relation is reflexive, anti-symmetric, and transitive on a set S, then it is called a partial order NS on S. Perfect. We can talk about many examples. We can introduce, and then the best learning is through the examples. So let's talk about them. Okay. 1. We have a relation R on the set of integers defined by A comma B is inside Z in cross Z, given that A minus B is less than or equal to 0. This is the relation. We show that R is a partial order on Z. Show R is partial order on Z. Now, first we know that A minus A is less than 0 or equal to 0 for all A in Z. Thus, A comma A is in R for all A in Z. So R is reflexive. Okay. For anti-symmetry, let A comma B comma A are in R. Then A minus B is less than or equal to 0, comma A is less than or equal to B. And B minus A is less than or equal to 0, i.e. B is less than or equal to A. This implies A is B, because this is the way we show how 2 things, at least numbers and the sets, are equal. So this implies A is B. And if A is B, we will have R is anti-symmetric. Perfect. And to show, finally, we show that R is transitive. To show that, let A comma B comma B comma C in R, then A minus B is less than or equal to 0 and B minus C is less than or equal to 0. Thus, A is less than or equal to B and B is less than or equal to C. This implies clearly that A is less than or equal to C. And so A minus C is less than or equal to 0. Hence, A comma C is in R. Thus, R is transitive. Consequently, R is a partial order on Z. Perfect. Now, we can show another example. That let's say R is a relation on N. So let's denote R by A comma B inside N cross N, such that A divides B in N. N is a natural number set. We need to show R is a partial order. Show R is partial order on N. So for the reflexive T, let A is a natural number and A is 1A. It divides itself. So A divides itself and A comma A is in R. So R is reflexive. Antisymmetric. Antisymmetric. Let A comma B, B comma A is inside R. Then A divides B and B divides A. Thus, B is AD and A is BC for some C comma D inside the positive integers. Okay, therefore A is BC, which is ADC. And so 1 is CD. Since C comma D are inside the positive integer set, and their product is 1, it follows that they both are equal to 1. If they both are equal to 1, we will have, hence A is B and R is antisymmetric. We have transitivity. Transitivity, so for that we relate A comma B and B comma C are in R. We will say A divides B and B divides C in N. Thus, B is AN, comma, C is BM for N and N inside the positive integers. This implies that C is BM, which is A and M, and since M comma N are from positive integers, Mn or Nm is also a positive integer. It's also a positive integer. Thus, A divides C in N, and A comma C is in R. Hence, R is transitive, and consequently, R is a partial order. Partial order on N. Perfect. Now, another example which can help us to understand that more clearly. So let's talk about other example. We have a relation R A comma B inside over the positive or the integers where A divides B in Z on Z. This is a relation on Z. And in the previous example, we show that R is reflexive and transitive. So R is reflexive and transitive by example 2. Now, since 6 can be written as -1, 6, -6, and -6 can be written as -1, 6. Then 6 comma -6 is inside R, and -6 comma 6 inside R. But we know that 6 is not equal to -6. Thus, R is not anti-symmetric, and this proves that R is not a partial order on Z. It was partial order on the natural numbers, but it is not a partial order on Z. To further understand this concept, let's define example 4. We have a set S. Let S be a set, and P of S is the power set. Let R be a relation on power set given by R be a relation on power set that it takes two sets from the power set and makes an ordered pair. Given that A is subset of B, this relation is on the power set of S. Okay, we show that R is a partial order on P of S. To do that, since we know every set is a subset of itself, so R is reflexive. Because A comma A is in R for all A in the power set of S. And anti-symmetry, let A comma B and B comma A are in R. That shows that A is a subset of B and B is a subset of A. So A is B. Because this is the condition by which you show A is B. So R is antisymmetric. And the last part is to show that it's transitive. We show that we consider let A and B comma B comma B comma C are in R. Then by definition, A is subset of B and B is subset of C. So A is also subset of C. And thus A comma C is in R. Hence, R is transitive. Consequently, R is a partial order on P of S. The partial order on a set is usually denoted by a symbol. So a partial order on a set S is usually denoted by this symbol. Instead of writing this inside this, we shall write. So we will write for the partial order as A is this. If we write this, then you can understand that there is a partial order between A and B. Okay. Definition. One 1.4.6. A set is together with a partial order is called a partially ordered set. Ordered set. Or you can also say poset. The definition of algebra. In the algebraic theory, you can say it's poset. Similarly, another notation point, if S is a poset, remember this word, I'll say if any set is a poset, then it is a partially ordered set. With the partial order, with the order with the partial order this, then we will write S like this. So there are names for every partial order. So in example 1.4.2, so that is in example 2, in example 1 actually. In example 1, R is a partial order also, and this relation is less than or equal to relation on Z. And in example 2, R is also a partial order. We call this the divisibility relation on N. And N together with the divisibility relation is a poset also. And in example 3, we find that Z together with the divisibility relation is not a poset because R was not a partial order on Z. Then the partial order in example number 4 is known as set inclusion relation on the power set P of S together. So the power set together with the set inclusion relation is a poset. Now, another point is if we have a set S, let S be a poset. So it has a partial order on its elements. And we take two elements from this set. If either A is less than or equal to B or B is less than or equal to A, then we say that A and B are comparable. Consider any state if you can write either A is less than or equal to B or B is less than or equal to A, then you can say A and B are comparable. So you can also ask the other way around. When the elements inside a set are comparable, when there is a partial order on this set, or the set is opposite, then the elements inside it can be comparable, are comparable. Another definition, which to define linearly ordered set or a chain. So let's define that. Definition for 4.7, a partially ordered set with this inclusion relation, with this less than or equal to partial order, is called a linearly ordered set or a chain if for all x comma y inside this set S, either x is less than or equal to y, or y is less than or equal to x. And then a set which has a partial order on itself is linearly ordered set if the elements inside the set are comparable. So that is the condition, that partially ordered set is linearly ordered set if the elements inside it are comparable. Okay, we will give one example for that and then in the video. So let's define an example. So we say number 1, Z together with the less than or equal to partial order relation is a chain. Okay, so yeah, we have defined it. We have written it's a chain also. The other name is chain, or a linearly ordered set is a chain. Okay, number 2, and with the relation R such that A divides B and N is a chain. Is not a chain. Is not a chain because neither 3 divides 5 nor 5 divides 3. Neither 3 divides 5 nor 5 divides 3. So 3 and 5 are not comparable. Remember, this sign over here, it's not just a less than or equal to sign. It is the sign which defines the relation inside the relation, which is the property in the relation. So if this sign is the property in the relation, in the Z, the relation we have is that we take 2 elements, we create an order pair, and then we say A is less than B, less than or equal to B in Z. That's why we have Z as a chain. But Over here, in the second example, the relation is this. We are taking two elements from N, and then we are saying A divides B. So, not all the elements inside the natural number divide each other. That is why we cannot say that N with this relation is a chain or linearly ordered set. So that's why we are saying that N is, because these elements are not comparable. Okay, number 3. We have a set with more than one element. So the set S have at least two elements. Then the power set of this S together with the subset property, inclusion relation, with the relation R, which takes subsets from this P of S cross P of S, and say that A is inside B. A is a subset of B. Is not a chain. Is not a chain. Because if A and B are distinct elements of the set S, then neither the set is subset of this set, nor this set is subset of this set. So these two sets are not comparable. That's why this power set with this inclusion relation is not a partially linearly ordered set. Perfect. We'll take the leave here and we will come back in the next section for this partially ordered sets. Thank you for watching and hope you will subscribe and like and share for the next videos, because after this series of basics on this group theory, I will record videos on group theory.